So earlier I talked about a lot of questions that we could ask about counting number fields, and then I had a bunch of questions about counting class groups and averages of various functions over class groups. And so now I want to talk about actually a relation between counting number fields and class group averages. And I'll talk about this first in a very specific example. Okay, so let K be an imaginary quadratic field. So these were the kinds of fields that we were asking about the distribution of their class groups. That was the subject of the questions I was asking there, and then the Cohen-Lenstra heuristics, which give conjectural answers. One of the functions that you might ask for the average value of that function on your class groups is the number of surjections to a particular group. And we'll see here in this example that it's not just some random function, it's one that has a lot of meaning for us. So surjections from the class group of K. Now I'll do some specific example here. So to Z mod 3, the cyclic group with 3 elements. So surjections from the class group to Z mod 3. So another way of saying that is Z mod 3 quotients of the class group. These, by class field theory, correspond to unramified Z mod 3 Z extensions L of K. So to unram Z mod 3 Z extensions. So I mean L over K is Galois with Galois group Z mod 3, or Z mod 3 sitting inside of S3 if we're thinking of it as a permutation group, like we were talking about Galois groups the last time. So I've got here my K, which was imaginary quadratic, and a surjection from its class group to Z mod 3 gives me an unramified Z mod 3 Z extension. So also, class field theory tells us that L over Q is Galois with Galois group with L over Q is S3. Now, L over Q is, of course, degree 6, so its Galois group should be a permutation group on 6 elements, so its Galois group as a permutation group is S3, which sits inside S6 by its action on itself, the regular representation. That's the there. So if this already you can start see a connection, which if we wanted to know about the number of these surjections from the class group to Z mod 3, because we were averaging that over quadratic fields, first we count the surjections, put that in the numerator, we count the quadratic fields, put that in the denominator to get the average. That counting these surjections amounts to counting these L over Q that are degree 6 Galois with Galois group S3, and moreover unramified over their quadratic extension, which it is imaginary. So to actually realize that that's the exact counting question we have to also note that conversely, any L over Q S3 Galois sextic with quadratic subfield K with L over K unramified arises this way. So counting these surjections from the class group via class field theory is now just a question about counting Galois sextic extensions of Q. And moreover, since L over K is unramified, the discriminant of L is this, basically the same data as the discriminant of K. I think it's the cube. So when we say we're counting things up to discriminant X, we were going to be averaging our class groups for K up to discriminant X. That's going to just be the same as counting fields up to discriminant X, all just shifted by cubing things. So, and these conditions, this condition that L over its quadratic subfield should be unramified, those are local conditions at every prime P on this field L, and that the quadratic subfield should be imaginary. That's a local condition at infinity on L. So we see that in fact, counting these L's is exactly the sort of question that we had before, and in fact, there's one more translation we can do. Also, so in this, I'll draw the diagram here. In this field diagram, there's one other field. There's by Galois theory, there's also the cubic sitting inside here, the non-Galois cubic. Maybe I'll call it K3. Okay. So also, well, there are actually three of them. There are three conjugate cubic fields here. So each L has these exactly three conjugate cubic fields, and if you have a non-Galois cubic, you can get such an L. So also we can use this diagram to translate this into a question about counting not Galois sextic fields, but Galois or non-Galois cubic fields. So we can turn this into a question about counting non-Galois cubics by counting our K3s instead of our L's. We still need to impose all the local conditions so that when we start with the K3 and we make the L over K will be unramified and K will be imaginary quadratic. But with all those conditions, we can put those conditions on the K3. And so now we see that this particular average of averaging the number of surjections from the class group of K to Z mod 3 can be translated into a question about counting certain cubic number fields. So that's one reason that these surjection averages are particularly nice, is that they all have these similar translations. And so this is just one example of a more general phenomenon. I think there's some exercise in the more general case in the notes. Okay. So this average also happens to be basically in this imaginary quadratic Cohen-Lenstra setup that I've talked about. This is the one thing that we actually know. in all of the questions you can ask about class groups, imaginary quadratic number fields. I said the Cohen-Lenstra conjecture would be that this average is 1, and that's actually a theorem of Davenport and Heilbronn that we will get back to at the end of these lectures. So this example is special only because it's the one place that we actually know anything. Right. So we've talked about questions of counting number fields and questions about counting class groups. We just talked about how some of them are related. And the next thing I'm going to head for is to try to talk about, I said that Cohen and Lenstra had these conjectures that at least let us guess how class groups are distributed, what the statistics of class groups are like. And I eventually want to tell you about some really more thorny, tricky conjectures that tell us how we might answer the questions of counting number fields, what we would conjecture those answers to be. But before we can even really make sense of those conjectures in a reasonable way, we're going to have to build up a few more tools. So that's what I'm going to do next. All right, so our first tool, I want to talk about Galois permutation representations. So actually, instead of counting number fields, it's maybe more convenient to think about counting certain Galois representations that are really the same sort of thing as number fields. So I'm going to want this for Q and also QP, so I'm going to state it over a general field. So for a field F, I'm going to write GF for the absolute Galois group of F. So that's the Galois group of separable closure of F over F. So we're interested in the cases, especially Q and QP. So for example, GQ is just the Galois group, Q bar over Q. We already talked about F algebras, at least in the case when F was QP. So these are F algebras that are direct sums of separable, I only care about characteristic 0, I like to say things exactly, but so finite, separable field extensions F. And in fact, so a Galois permutation representation, it's an action of the Galois group as a permutation group on a finite set, or another way of saying that, it's a continuous homomorphism from GF to the symmetric group. So that's a Galois permutation representation, and such things up to isomorphism, and we already mentioned the kind of isomorphism of a map here. It's by conjugacy on SN, or just relabeling the in objects that you're acting on. So there is a bijection between Galois permutation representations and degree in F algebras. So well, here, maybe I'll say one more thing here, and then we'll talk about the examples. And in this example, the transitive permutation representations, i.e., the ones that have a single orbit, correspond to field extensions. So we already saw sort of one piece of this, so I just want to tie this together with the piece we talked about, which is if we have, say, say in our, if we have K over Q, a degree in number field, right? So that's an example of a degree in étal Q algebra. And so in particular, it's a field extension, so that should correspond to a transitive Galois representation. Well, we talked about the map from the Galois group of the Galois closure of K over Q to Sn via the action on the maps from K into Q bar, and of course the Galois group of Q bar over Q has this quotient. So this composite here, this map, so it's just given by the action of this Galois group. So it's given by the action of GQ on the N maps from K in to Q bar. So if you have a map from K into Q bar, and then you have an automorphism of Q bar, that gives you a different map from K into Q bar. So that's how the Galois group acts on these N maps, and that gives you one example of how you take a degree in algebra and you get a Galois representation. So that's actually pretty much the more general picture. So if M is a degree in étal Q algebra, right? So there are N maps from M to Q bar. Now, we don't want to get scared by the sort of étal Q algebra. Remember, this is just, say, a direct sum of field extension. So maybe it's K1 plus K2 plus K3. So say Ki is degree Ni, and the sum of the Ni's is N. That's what makes M a degree in étal Q algebra. So these K1, K2, K3 are just number fields of various degrees, and their direct sum is a Q algebra. And here, what are the N maps? The N maps from M to Q bar. Well, there are the Ni maps from K1 to Q bar, because K1 is a degree in number field, so it is N maps into Q bar. Right, you take a generator, we did this before where we wrote the field as Q adjoint theta for some generator field theta, and then you can just map theta to each of its conjugates in Q bar. So, sorry, they're in one of these maps, and then it's in K2 and K3 just to 0. Right? So, and then there are the maps that send K2 to Q bar, and the maps that send K3 into Q bar, right? And each of these send the other number fields just to 0. So they pick out, each map picks out a field and maps it in and squishes the other one, send them to 0. So now we've got all these maps. These are all maps from N into Q bar. So GQ, the Galois group of Q bar over Q, acts on these N maps, right? You take one such map, then you act by GQ and you get a different map. But here, for example, in this case, we're never going to turn a map that sends K1 in it injectively and kills K2 and K3 into a map that, kills K1 and K3 if all we do is an automorphism of the Q bar. So in this example, we see that the map here has, in the example, the map has 3 orbits. So it's not transitive, which is what we expected. And you can sort of see here, I think, why the field extensions exactly correspond to transitive permutation representations. And here we have an example where you have a permutation representation of the Galois group that's not transitive. It has 3 orbits, and that corresponds to an étal extension that's not actually a field extension. So So maybe I'll just briefly indicate going back. So given a continuous homomorphism from GQ to S in the permutation group, let HI in GQ be the stabilizer I, not as I runs from 1 through n, but as I runs over an element from each, over one element, let me say one element from each orbit. So if there was just one orbit, if this was a transitive permutation representation, you could just take one. And you just have one subgroup here, where you're going to have a Galois representation with 3 orbits. You would take one element from each orbit, and then look at its stabilizer, so then you get the 3 groups. So for each of these HIs, since they are subgroups of the absolute Galois group by Galois theory, they correspond to Ki number fields, number extensions of Q, and then the étale extension from this permutation representation is just the direct sum of these Ki's. Okay, so that's just how you go back. So, a little bit, I said we have a bijection between isomorphism classes of, you can think of them as maps from that absolute Galois group to the permutation group Sn. It's perhaps better to think of them as actions of the absolute Galois group on a finite set of size n, and there's a bijection between these objects and degree n étale F algebras. And so we're going to use this bijection in both the cases where the field is Q and then also where it's QP. Okay. So maybe I'll just make one more remark here, which is that you can, I mean, not so surprisingly, that you can get, you can recover. So we're interested in things like counting actual field extensions by their discriminant. So we need to know what their discriminant is. And so it's important that in this bijection, for example, you can recover, in fact, perhaps more easily than from the field, you can cover, for example, the discriminant of an étale extension from the map in some reasonable way. We'll see more specifically examples of that, but that's going to be important. And so that just means that these questions about counting number fields up to discriminant x, we could just translate them all into this language of counting Galois permutation representations. And if we were just counting number fields, then we're just going to be counting transitive Galois permutation representations up to discriminant x. All right, so that is one tool we're going to use to even be able to raise some conjectures and also to answer some of the questions. Okay, and now I'm going to talk about another tool, and then we'll get to put these two tools together. So the next tool is Tauberian theorem. So this is a pretty standard kind of method in analytic number theory, and it says that if we have some numbers and we want to understand how they grow, we can make them coefficients of analytic function and translate that into a question about understanding the function. So let me maybe write a specific theorem. So I think I have a more general theorem in the notes, but I'll just stick now for an example. So let me define a Dirichlet series. F of s to be the sum of an times n to the minus s. So an, I'm thinking of as some numbers that I'm interested in. So an's are some numbers that I'm interested in. I'd like to know how those an's grow. All right? And I put them all together into this gadget, which at first is just you could even think of as just a formal kind of power series. F of s. So it's just a sort of generating function. I put each of the an's with n to the minus s. But now, I'm going to further suppose that this function has some sort of reasonable analytic behavior. So, with, say, f of s convergent for real part of s, say greater than 1. Okay. And analytic continuation to real part of s, at least 1. Okay, so just thinking, reality check, what does that mean? That doesn't sound like we did much. Well, to talk about an analytic continuation to this thing with this closed boundary, we actually, we need it, a little past real part of s equals 1, because we need an open set to be analytic on, but I haven't said we have to get any certain amount past real part of s equals 1, and of course I can get different amounts past for every sort of location in the complex plane. Right, so if f, or in particular, I mean, you have to say the continuation. So if the continuation of f has a simple pole at s equals 1 with, oh yeah, maybe someone just said I should have said meromorphic. Yeah, thank you. We often talk about so meromorphic continuation. So if f has a simple pole at s equals 1 with residue r, then, okay, so here's the sort of magic. It tells us that these partial sums of the coefficients are like Rs. Okay. So the ANs were maybe some things that you wanted to count, and they each had an integer attached to them. For example, AN could be the number of number fields of discriminant n. Right? So it's some object that you want to count, and we want to count them asymptotically, how many of them there are from 1 to x. So we're adding these all up from 1 to x. And this theorem says that if we can do some sort of complex analysis and understand a rightmost pole of this function, that we can actually get a theorem, an asymptotic theorem about how these partial sums grow, just in terms location of the pole and the depth of the pole and the residue here. So you can soup this up in a lot of ways. So first of all, you can talk about not just poles at s equals 1, but poles at other locations. That will affect the exponent of the x here. You can also, instead of having simple poles, you can have multiple poles that adds log factors to this. So like if you have a double pole at s equals 1, you get like something like x log x. If you get your analytic continuation a little further, you can actually get a power savings error here. And so I state a more general, though definitely not the most general form of such a theorem in the notes. And so this theorem suggests the general strategy, which is anything you want to count, just put it as coefficients of a Dirichlet series, and then you just need to, do some analysis on the function, and out pops the answer to your counting question. So I think that at first it makes it seem almost too easy. But just let me remark that, so in general, so finding meromorphic continuation of a Dirichlet series that you wrote to count some things can range from hard to impossible. I suppose sometimes it might be easy, but in general, it ranges from hard to impossible. Okay. Just to give you a sense, like a nice example is the L function of an elliptic curve. You can write down nicely as a sort of Dirichlet series, just counting some simple things like the number of points that an elliptic curve has mod each of the primes. But it's a major achievement of modern number theory that such things have meromorphic continuations, and that's even an example where you have some sort of program that tells you where to look for the meromorphic continuation. In general, this did not just make all problems easy. I just want to emphasize. And then secondly, even if you have a continuation, so for example, in the case, so even with a continuation, the analysis of the poles can be hard. So, for example, in the cases of counting quartic and quintic number fields, so these would be the cases. So here, let me just say, for example, say let AN be the number of quartic or quintic number fields of discriminant n. So in these cases, actually, it was known that there was an analytic continuation of the Dirichlet series that you would write down. And people thought that, well, okay, now we've got the analytic continuation, we just need to sort of figure out the poles and do some analysis and apply a theorem like this, but it turned out to just be too hard. And very smart people worked on it for 10 years and were unable to make this kind of approach work out. Okay, so yes. Oh, yeah. yeah, sorry, definitely, absolute. Yes, so that you actually have an analytic function. Yes, thank you. All right. Thank you to my analysts in the audience that are keeping me honest. All right, so, okay, so now that I have warned you that this theorem will not, in fact, solve all your problems, I'm now going to do an example where we can actually use it and get some results. So I'm going to now talk about counting abelian number fields. So, okay. So I'm going to start by actually counting quadratic number fields, which, and I will, this, actually, if you combine this with Jordan's talk, maybe we will have two really difficult ways of counting square-free integers. In case Bjorn's easy proof wasn't enough for you. So to count quadratic number fields, you could essentially just use the fact that you know what all the quadratic number fields are. They're given by their discriminant. And except for some issues at 2, the discriminants are essentially the square-free integers, so you need to deal with some things at 2, but essentially it comes down to counting square-free integers, which Bjorn did for us. But I'm now going to do it a harder way, because it's a way that actually can work more generally for other number fields whose Galois group is an abelian group, which is what I mean by abelian number fields. I mean Galois with abelian Galois group. Okay, so I'm going to do this. So using class field theory, all right, so to start with this, all right, so what does class field theory tell us, for example, about quadratic number fields? So I'm going to use JQ to denote the Adele class group of Q. So that's the product over here. This is a product over places, so I'm including the infinite place of QP star. Remember that Q infinity was the real numbers. And it actually needs to be a restricted product, so that there's a little dash there. I say more in the notes, but you need your entries to be actually integral. So in ZP star at all but finally many places. But let's not worry about that so much and just think, okay, we've got a bunch. For every place, I've got an element of QP star, and then I mod the whole thing out by Q, because of course if I have a rational number like 6/3, for every place, 6, oh, that was strange actually. Wow. How did I come up with that? Okay, let's see. 7/3. We got 7/3. If I rational number like 7/3, it sits in QP star for every P, so this sits as a subgroup here of this multiplicative group, and this is the Adele class group, right? Class field theory tells us that okay, so homomorphisms from GQ to Z mod 2Z, or of course this is the same as S2, so those are my quadratic number fields, since I just talked about the correspondence between permutation representations and field extensions. So that these correspond to continuous homomorphisms from the Adele class group. Okay. So there are more details in the notes. These groups aren't the same, but the finite completion of this is this. So when you're taking these finite quotients, as far as finite quotients are concerned, this it acts the same as the abelianization of this. So maybe more precisely, as far as abelian finite quotients are concerned, these two things are the same thing. So if you have seen class field theory in a different way, I encourage you to think about how the way that you would say use it to classify quadratic extensions can be translated into this language, because this is very convenient. So to count quadratic extensions, I want to count maps from JQ n to Z mod 2Z. Okay, so I want to count maps from JQ into Z mod 2Z. So if I have, say, I'll call them phi. Okay. So if I have such a phi, it restricts to, I could just see, say, where does it send all my my integral points, so my units, really, I should say my units, okay. And so here I'll use Z infinity to, maybe Z infinity star to denote positive reals. Okay. So I've got a map from all these QPs into Z mod 2. I could just say, well, where does it send all the ZPs? So in fact, so any phi0 extends uniquely to a map from JQ to Z mod 2Z. And here, more details are given in the notes, but briefly I should just say, well, if you know where all the p-adic units go for every p, the only thing that you don't know, let's say in QP, the things that aren't p-adic units are just generated by p. So you need to know where, say, so this is, say, in the QP place, a P in the QP place, you need to know where this goes. But the fact that this map has to factor through Q bar, that tells you that's the same as where, say, if you put in a P inverse in all the other places, goes. And now this P inverse is actually a unit in all the QPs, in all the other places besides the QP place. So this element is actually in our product of ZP stars. So phi0 is defined here. So that shows you how you could, that shows you the unique part, actually, of this extension. And if you just think a little bit carefully, you can actually see that that's a well-defined extension. So in fact, it extends uniquely. So, okay, I was going to count maps from JQ into Z mod 2Z, but I saw that those are the same then as maps from this product into Z mod 2Z, all right, because those each correspond to a single map JQ into Z mod 2Z. So now I'm counting maps like this, and now there's no longer a quotient by Q here. That's important, because now a map from this product of ZB star into Z mod 2Z, it's just a map at each place. So i.e., I'm counting these for each p. Okay? Now, when p is not equal to 2, then there are 2 such maps. So one trivial, one not. They factor through z mod pz star. When p is not 2, they have to factor through this because the kernel of the map from zp star to z mod pz star is a p pro p group. So they would have to factor through this. And this, of course, is cyclic, so the generator either goes to 1 or goes to 0. And if p is 2, there's actually 4 maps. What's great about this is, we originally cared about our discriminant of the number field. I said, well, you could get that from this data. Well, we can chase that along everywhere. We can get it from this data. Actually, we can even get it from this data. It didn't matter where the rest of the things went. It just mattered where ZB star went. These are the inertia subgroups in the Galois group. So, in fact, the trivial map, of course, corresponds to a trivial extension that is discriminant 1. So this here has discriminant p, and these 4 maps are a little more complicated. They have discriminants 1, I guess, 4, 8, and 8. Okay. So, all right, I will. So we can finish by putting these into now a Dirichlet series. So the Dirichlet series, where I take the product over here. There's only one map when p is equal to infinity, so that sort of fell off. So yeah, maybe I should say, okay, p equals infinity, one map. Okay, doesn't really matter. Okay, so if I take the Dirichlet series and, okay, not a 2, I just do this, and then at 2, I've got 1 plus 4 to the minus s plus 8 to the minus s plus 8 to the minus s. If I multiply these out, I'm then counting all possible maps here, so those correspond to all quadratic extensions by discriminant. So this is the Dirichlet series that AN equals the number of quadratic fields with absolute discriminant n. So, so we can now apply the Tauberian theorem to this Dirichlet series. So we need an analytic continuation or meromorphic continuation to do that. Luckily, this part looks a lot like something that we actually know. So this is, if we sort of forget about the 2 part and we make it what it should have been, then this is zeta of s over zeta of 2s. Zeta is the Riemann zeta function. So, hooray, we have, because now we've written everything in terms of zeta, we have all the meromorphic continuation we want, and we know all the locations and residues of the rightmost pole. That's all we need. That's good. Okay, poles, rightmost poles. And then we can conclude despite all this nonsense at 2, I believe we actually get here that asymptotically we have 6 over pi squared x. So, very popular number.